Okay. Hello, everyone. Today, I would like to present to review the paper. The title is Weld defect identification and characterization in radiographic image using deep learning. Okay, the author for this paper, Abi Basal et al. And the first one, I want to introduce myself. My name is Jeffrey Sutanto. I'm a student in nuclear engineering from Bandung Institute of Technology (ITB) and as employee and National Research and Innovation Agency of Indonesia (BRIN). Next, this is the contents that we should discuss together. Consists of abstract introduction, CNN-based approach for Weld defect classification, comparative analysis of Weld defect classification, challenges and future scope, and the last one, conclusion, and the information in reference. Okay, next, the abstract defects. Mostly, as we know, a defect it can be happen from welding, from forging, and casting. In this paper, just describe about weld. So in the welding, there are so many defects, various of a defect. For its inclusion, cracks and pores are example of welding joint imperfection. So automatic weld defect detection is needed by analyzing the image obtained directly from digital radiographic system. This paper used a unique image-based approach to small batch of X-ray imaging dataset to investigate a potential solution for weld defect identification. This article compared a deep learning network performance for various parameter and hyperparameter combination. Also, it compares a traditional approach of defect detection using manual inspection method, feature-based defect identification, and finally, a deep learning based approach of several types of weld defects in various industrial application. This comparative analysis concludes that deep learning based approach have achieved more accuracy as compared to conventional techniques. This research paper also highlights a few challenges and future direction in welding area. Okay, this is the introduction. Welding is the most extensively used joining a technology to affix metal components in various industrial applications permanently. It is required to investigate the quality of the weld joint before authorizing industrial application, such as gas pipelines, oil pipelines, vehicles, steam turbines, ship, and other sort of metal structure. We can call it the concrete. And also many papers right now discuss about the plastic in industrial application. Okay, this investigation is required for recognizing and localizing several types of weld defects such as porosity, surface cracks, inclusion, undercut, poor fusion, and poor penetration. The weld defects can significantly impact the welded joint reliability, durability, and mechanical properties such as stiffness, toughness, and strength. Okay, as we know, to analyze, to testing something, we need to, we can call it a two-way non-destructive testing, NDT, versus DT, destructive testing. Okay, what is DT? DT is a technique for testing weld by breaking, which is proposed to determine the strength of the welded specimen. Okay, in the right side, there are examples for destructive testing, static testing, impact testing, cyclic testing, such as tension test, compression test, shear test, hardness test, group test. Okay, what about the NDT, non-destructive testing? Based on ISO standard 9712, there are 10 methods in NDT. Visual testing, radiographic testing, ultrasonic testing, penetron testing, magnetic testing, and etc. Okay, what is the NDT? NDT is a way of inspecting an object to detect weld defects without causing any damage to the object under test or inspection. So we focus on in NDT is there is no cause any damage to the object under test or inspection. That is NDT. Next, in conventional radiography, we can call it the traditional radiography. The component to be examined is exposed to the X-ray, and the radiographic image are recorded on the X-ray sensitive film positioned behind the component. Traditionally, visual inspection of radiographic image are accomplished by fault detection engineer with long-term experience. Okay, this manual process can be subjected to several factors like capture defects of small dimension, undetectable nature, and some noisy and low contrast radiographic image, making it very challenging to find them using conventional techniques. Also, it should be highlighted that accident might happen due to human factor like exhaustion, carelessness, lack of training, or a combination of these. However, defect detection by manual inspection methods is usually time-consuming, expensive, prone to error, and ineffective. Therefore, developing a novel defect detection technique that is highly effective, accurate, and affordable is crucial. Okay, the feature best defect identification has gained increasing traction and gradually replaced traditional manual inspection due to the rapid advancement of digital image processing techniques and machine learning. We can call it how to be from the traditional, the conventional techniques to be digital image processing techniques. Okay, four significant challenges occurred. First, a single detection task may encounter various problems, each with a unique set of features. Complexity of the weld defect identification problem. Secondly, defect ordinarily present in a wide range of categories and features. It is more difficult when faults appear as patch of poor contrast, uneven brightness, or asymmetrical shape. Third, gathering large quantity of weld defect samples in industry, particularly some rare ones, result in severely unbalanced and expensive weld image data sets. Okay, finally, there is a chance that some weld defect data will be lost during feature extraction. CNN convolution neural networks can overcome such constraint. This is the primary motivation toward this effort. Okay, this is the feature CNN-based approach for weld defect classification, data collection, image pre-processing, and defect classification and weld defect. Maybe later I will tell more deeply. Okay, next. Although there are other excellent survey studies in the literature in the field of the weld defect detection, it like a comprehensive review paper that covers the compiled study of various weld defects on benchmarked dataset using traditional and deep learning. Okay, in this paper, we discuss the desired architecture, characteristics of image classification execution, welding defects, and the comparative analysis of weld defects classification, challenges, and future scope. Okay, the second chapter, CNN-based approach for weld defects classification. Well, defect classification consists of data collection, image pre-processing, and defect classification. Okay, figure one illustrate the basic workflow diagram for the well defect classification process. So, in the first step, data collection, there is a radiographic well defects image, okay, a data set, and continue to the image of pre-processing, grayscale compression, binarization, noise filtering, and training or testing data set, and also to be defect classification. There are various the type of defects like porosity and the others. Okay. Um, In 2.1 data collection, this paper presents a benchmark data set consisting of 90,407 or more X-ray image. Okay, based on BAM, Brewster ankle microscopy, was first used to take X-ray picture. These images are arranged in an X-ray database. This database of X-ray image is popularly known as the GD-X-ray database, which can be utilized to develop a well-defined classification algorithm. Due to the presence of the benchmark datasets, we do not require any expensive X-ray equipment to be purchased. Okay, five categories of X-ray image are presented in the GD X-ray database: casting, well, luggage, and natural entities. Each class has several series, and every series contains a numerous X-ray image. We discuss the well category for well defect classification. As you can see in the picture, um, okay, the sample image of well GDX database in A subset for subset of five X-ray image. Okay, we make it a W1 series and B subset of five X-ray series, and C subset of X-ray five X-ray image W3 series. The picture. Okay. The class well consists of 88 images organized into series, namely in the previous one, W1, W2, and W3 as shown in the table 1 for the series, and consists of for W1 10 image, W2 10 image as well, and for the W3 68 image. So the totals is 88 image. Okay, this is the representation of well class of GDX-ray database. Okay, we talk about the image pre-processing. Digital radiography images frequently exhibit low contrast, noise, and uneven grayscale distribution. Two, while the effect detection was influenced by a radiography picture quality, particularly for those minor errors easily masked by background noise, many processing techniques were used to resolve the impacts of these issues. To prevent losing important information, it should be underlined that processing techniques must be used carefully. Important information for the discrimination of the defect types includes the initial shape and brightness distribution of the weld defect, which may be absent. The image preprocessing techniques mainly involve cropping, resizing, grayscale comparison, noise reduction, and binarization or thresholding. Okay, next we talk about the defect classification. Another critical aspect affecting the effectiveness of defect classification is based on the selection of the classifier. Since the majority of the features of the weld defects are extracted manually, several researchers focus on automatically detecting welding defect using a learning approach. Convolutional neural network (CNN) application have begun to rise. Okay, as shown in the figure 3, the CNN deep learning model is based on the hypothesis that biological neurons communicate with one another to transmit information. CNN outperform machine learning models in image classification as well as objective recognition. Okay, CNN used the back propagation algorithm to learn the network. Forward propagation analysis is used to determine the loss function value. The back propagation algorithm is then used to adjust the biases, and the convolution kernel's connection weighed up to the loss value reach the desired level. By repeatedly updating the manner described above, CNN improved its classification accuracy. Usually, the researcher select weld defects to be classified as porosity, lack of penetration, select inclusion, lack of fusion, and crack. Okay, this is the various kind of type of defects. Okay, this is the architecture of the CNN model. Feature extraction, input, feature mapping, and also classification to be output 0 and 1. Okay, comparative analysis of weld defect classification. Okay, based on Ma Dayuan et al. Research, employees CNN to categorize the TF spectrum graph and detects weld porosity. The CNN model for porosity detection takes the TF spectrum graph as a group of RGB, red, green, blue image, and categories them into two levels. Level 0 represents no porosity, and level 1 indicates porosity. Their CNN model obtains detection correctness for porosity defects 93.15% and average classification correctness of 96.13%, which can fulfill the specification during manufacturing. Okay, based on the research, Stephen et al. Have successfully classified the weld defects of radiographic weld defect image using the CNN model. They classify 4 primary weld defects: gas pore, cluster porosity, crack, and tungsten inclusion. Their proposed method gained 99% training accuracy and 95% validation accuracy. Okay, based on the research, Takalakapali et al. Used a 78 X-ray image from the GD X-ray database of X-ray image to prepare the dataset. Their dataset will only contain the following classes: good well or no defects, cracks, porosity, and solid inclusion. Training accuracy for their model was 93.17% and validation accuracy was 91.14%. Okay, based on the research, Yang Liu et al. Collected 220 sample image with 5 categories of welding defects, 50 porosity image, 50 select inclusion image, 50 lack of penetration image, and 35 lack of fusion image, and also 35 cracks of image. 80% of the image of their dataset are selected as the training set, and the rest, 20% are employed as the testing set. Their model achieved an average testing accuracy 91.36% and training accuracy 97.95%. Okay, based on the research, Shiras et al. Use an UMAC1 scanner to obtain X-ray wild image. Their database is arranged in three different folders of X-ray wild image. Their network architecture is based on PGG with two additional convolutional layer before the max polling layer, batch normalization layer following the ReLU activation, and dropout layer after the max pool layer are also introduced. Okay, based on Osang Jin et al. Composed their dataset with a still five radiographic testing image. Their model classify in two defects, porosity and loss, like of slag. They attain a map of 0.532 for ResNet with data augmentation. Based on the research, Jiang et al. Identified a two problem in traditional CNN for dynamic adaptability of the pooling techniques and inadequate feature selection capability. Okay, based on the research, Umaydi et al. Constructed their welding image dataset with a total of 120 images, which are divided into four classes: porosity, undercut, over patterns, and good image. Each class consists of 30 images. 80% have 96 image of the data set used for training, while 20% have 24 image used for testing validation. The proposed approach successfully classified for welding defects with the validation accuracy 95.83%. Okay, this is the comparison of weld defect classification. The author Madayon et al., Stephen et al., Takala Pali et al., Yang Lu et al., Achimi et al., and etc. There is defects, the kind of defects, the data set, number of places, the methods that they use, and accuracy. Okay, next we talk about the challenges and future scope. Welding defects that occur during different welding processes are underfill, undercut, lack of penetration, lack of fusion, spatter, porosity overlap, slag inclusion, excess reinforcement, crack, and burn through, etc. Early researchers have identified some of the weld defects like crack, porosity, lack of penetration, etc. Some of the weld defects still impact the weld performance greatly, like weld spatter, excess reinforcement, etc. But researchers are not focused on the detection of this defect. Creating a data set for this defect is a big challenging task. Okay, furthermore, both the quality and size of dataset have a significant impact on the performance of deep learning models. It is challenging to obtain a reliable dataset for weld defect detection. To properly implement deep learning models in weld defect detection application, people frequently struggle to find a sufficient amount of data. In manufacturing, the number of parts that are defect-free is substantially larger than the number of parts that are defective. Consequently, the data containing defects is naturally small. The size of the data collection, including weld defect, can make localization and categorization of weld defect difficult. Okay, this is the conclusion. Examining the quality of weld joint is crucial to ensure the characteristic of the weld bed structure. The assessment of image executed by expert is inaccurate, time-consuming, subjective, and expensive. Therefore, many researchers have focused on automating the defect detection technique using computer vision. This paper provided guidelines for using digital radiographic images to detect weld defects. The technologies were implemented in stages as weld defect detection progressed. This research provided a literature survey on automatic defect detection based on deep learning techniques divided into the three steps: data collection, image pre-processing, and defect classification. Firstly, this paper described the benchmark dataset collection regarding the GDX array database. Secondly, we found that a few image pre-processing techniques, such as thresholding and noise filtering operation, upgraded the quality of the defect area. Afterwards, the benefits of deep learning models were examined and application of well defect identification were introduced. Lastly, a comparative analysis of well defect classification by various researchers is presented for future enhancements in this field. Okay, finally, this is the information about the reference. There are 33 reference for to review this paper. Thank you and have a good day. Thank you.